Okay, we're going to look at just one algebraic technique for solving differential equations. And this applies to a particular type of differential equation called separable. Some of you are going to go on and actually take a whole class in differential equations, and you'll find that there aren't very many general techniques. They all have to sort of fit a specific category. So this is one of them. So what does it mean to be separable? So consider a differential equation, something like y prime equals, let's just keep it simple, x over y. So again, the idea is some function. When you take x and you divide by the function, it's equal to the derivative of the function. Again, I don't really know what that function is yet, but this does turn out to be a separable differential equation. So let me demonstrate the steps. First of all, we want to rewrite in this notation, the Leibniz notation, if you are keeping track at home. But we want this dy dx notation. And we are actually now going to separate. So I guess step one, if it's not already in it, so put in that Leibniz notation where the derivative is written as a fraction, a change in y over a change in x. And then the next step is to separate the x's and the y's. And that's just algebra. So I'm going to take my previous line, I'm going to multiply both sides by y. So I get y times dy dx equals x. And I'm going to multiply both sides by dx. So, sorry, just to make that clear, here we're multiplying both sides by y. And now I'm going to multiply both sides by dx. And keep in mind that this derivative, dy dx, can be looked at as a fraction with two separate pieces, change in y over change in x, and we are just multiplying by the change in x. So we get a separated differential equation. All we've done so far is rewrite it algebraically. Haven't done any calculus on it yet. But notice that all the y's and dy's are on one side. All the x's and dx's are on the other side. And I don't know if your intuition is telling you what the next step is, but the next step is these both look like integrals. The next step is just to integrate. And we can do that if we have a y function and dy and some sort of x function and dx. We can treat those as separate integrals. One is an integral in terms of y because it's got dy. One's an integral in terms of x. It's got dx. Both these integrals happen to be really easy to do, so 1/2 y squared equals 1/2 x squared plus c. Technically, they both have plus c's. But since plus c is an arbitrary constant, you can move the plus c from the y's over to the other side. And they're not necessarily the same arbitrary constant, so they don't cancel each other out. But they can be combined into one arbitrary constant. Okay, we're basically done. This isn't quite solved for y yet. Usually when we have a solution, we like to say y equals. So let's multiply both sides by 2, finish solving this for y. So y squared equals x squared plus 2c. This 2c, think about that for a second. C already stands for an arbitrary constant. So what is twice an arbitrary constant? It's an arbitrary constant. So I'm going to replace this 2c with just a c. Granted, it's a different c, but it's arbitrary. So x squared plus c, y equals plus or minus square root of. Okay, that's the solution. I'm not going to check it, but you should be able to check that the derivative of this is the same thing, so y prime up here is the same thing as x over this. Okay, let's take a look at another example. So let's say you've got some function whose rate of change is equal to .04 times the function itself. This is something that essentially has a constant growth rate. This says whatever size the thing is, the growth rate is 4% of that. So this might be interest on a savings account that's at 4%, which would be really good. Or this might be population growth that's growing at 4% of the population. Whatever it is. Let's see if we can solve this as a separable differential equation. So let's write Leibniz notation, dy dx. Equals 0.04y. And let's separate this thing. So I'm going to divide both sides by y. And I'm going to multiply both sides by dx. Notice this is separated, right? There aren't any x's on the right-hand side, but all of the x's and dx's are on the right-hand side, and all the y's and dy's are on the left-hand side. So I am ready to go ahead and integrate this thing. Maybe to make the integration look a little bit nicer, I'm going to write this as 1 over y times dy. Maybe that's a little more comfortable. And this is just integrating a constant over here. So 1 over y, we know that's natural log of y. 0.04 goes to 0.04x plus c. And again, this is a solution to the differential equation. We just normally like to see the solution solved for y. So let's exponentiate both sides. E to that power and e to that power. So e and natural log cancel each other. You get y equals e to the 0.04x plus c. The plus c is in the exponent. This whole thing is exponent. And we can simplify just a little bit algebraically here. Let's do y equals e to the 0.04x times e to the c. I think we're more used to going this direction. Same base is multiplied. What do? Add the exponents. But if you have added exponents, you can also turn it back into same base as multiplied. And the last thing to point out here is that e to an arbitrary constant, guess what? It's still an arbitrary constant. So e to the c is just a new c, and I'm going to move it in front and say c e to the 0.04x. And there's my solution. If you did any exponential growth and decay in pre-calc, you might have already known that e to the 0.04x is 4% growth at a continuous growth rate. Okay, so those are a couple warm-up examples. We need to take a look at a couple examples of initial value problems and maybe some slightly more complicated integration as well. So we'll do that in the next video.